All right, so welcome to the status and trends in the HPC landscape panel. I'm Todd Gamblin. I'm going to be moderating. And we have a panel of experts up here to tell you what's going on in the HPC landscape and how it could affect software. So the questions I've asked all the panelists to think about their answers to are, first, what are your organization's main application areas and how will they change in the next 5 years? And how much of the workload do you think will shift to AI and other non-traditional HPC areas? What software problems that were issues 5 years ago have been solved or at least significantly mitigated? What are the biggest software pain points for your users? What are the gaps in the HPC software stack and how should it change to deal with new application areas and AI? And then finally, how could HPSF help? And so with that in mind, these are your panelists. So we've got Mike Kiernan, who is a principal technical program manager at Microsoft. We've got Dan Stancione, who is the director of the Texas Advanced Supercomputing Center. Heidi Paksan, who is head of technology and advanced computing and simulation at AWS. Sarah Campbell, who is a program manager at NNSA, who is, I guess, in space. So you see her on the screen sometimes. Jayesh Badwaik from Ulick Supercomputing Center, and he's a scientific employee. And Nur Fidel, unit head at CSCS. And then finally, Doug Jacobson, HPC software engineer at Google. And I went back in time and got a picture of Doug from graduate school to put up there. So that's, yeah, okay. Okay, all right. So with that, we're gonna start with Mike. I've got everyone's slides in here. They're going to give a brief statement, hopefully brief. You guys are going to be brief, right? So for their answers to those questions. And then we're going to take questions from the audience. You can see down at the bottom here on all the slides that there is a number. You can go to onlinequestions.org and enter that number there to ask questions while this is going on. And we will take audience questions at the end, and I will ask them to the panelists. So put the questions in there. Sorry for skipping ahead a slide. So we'll start with Mike. Here you go. Thanks.
Thanks, Todd. So Mike Kiernan, I work for the High Performance Computing Group at Microsoft in Azure Core, or as we're now known, the AI and HPC programming team. So you can imagine how things have changed over the past couple of years. So why is Microsoft here? We're here kind of on a scouting mission. So I'm here with Andy Howard, who's over here at the front. Andy's in the software engineering team, joined us with the Cycle Cloud acquisition at Microsoft. So we're here to really understand what HPSF is all about. I'm personally here on a bit of a shopping mission, looking for a programming environment, specifically an open source programming environment. That's something we've built ourselves. I'm going to talk a little bit about in my lightning talk later in the week. So what does Microsoft do in high performance computing? So we have a sort of traditional elastic computing InfiniBand clusters that we've been doing for many years. So we're on the sort of 5th generation of that type of system. New systems coming out, which is an HBM AMD platform with 800 gig InfiniBand. So it's just sort of rolling business as usual. What's sort of slightly less well known is some of the very large tenants that we're running for AI and also private supercomputing environments for some of the large tenants like the UK Met Office. So I'm based in Cambridge in the UK. So my team is the delivery team for the UK Met Office supercomputing system, which is currently an HPE Cray EX system. So maybe you may be surprised to know that we run Cray systems in Azure as well. Lots of other very large supercomputer class systems, which are mainly GPU systems, producing products, all of which everybody here is probably consuming in the form of different AI products from different vendors. So we also build software. The software that we run is generally, like Andy's team with Cycle Cloud, we're producing tools which can deploy infrastructure at scale in the cloud and then manage that infrastructure. Where we're not so strong in the HPC side of the house is in this application programming layer, and that's something that I think we're looking at having conversations here about, seeing is there a initiative that Microsoft could start and own. We don't want to just be a passive member. We want to actually make some broad contribution. So here to have those discussions. I'm waffling on, aren't I? In terms of answering these questions then. So I wrote these as I got off the plane just last night, so I got to remember what I wrote. So in terms of the main application areas and how they'll change in the next 5 years, a lot of the time we don't know what our customers are doing. So if we're not running POCs alongside those customers, the big tenants, obviously we're intimately involved in getting their applications running and performing at scale. A lot of the other sort of commodity platform that we're running, we may have no insight into what they're doing. Certainly what we can see is that the AI workloads have ramped up massively over the past 5 years to the point where they're hugely dominant. I can't give you any numbers on that. We don't disclose that sort of information, unfortunately. But what we would consider a large HPC system in the cloud is generally very small compared to the GPU AI training systems that are sitting alongside it, which can be, in the same machine room or more likely in another data center on the other side of town. So we've got lots of different types of infrastructure. In terms of the AI or HPC workloads transforming to become AI workloads, not so much. I think we're seeing a lot of R&D teams which are working usually separately from the HPC development that's happening in our customers, and they're tending to deploy to adjacent GPU infrastructure. Not really seeing those two workloads coming together just yet, but we do start to expect to see emulators starting to replace parts of the workflows and things like weather and climate modeling over the next few years, but that's not happening just yet. What software problems that were issues 5 years ago have been solved? From my point of view, not many. In fact, I think just the degree of problems that we have to deal with lots of different combinations of operating systems, different proprietary programming environments that we're having to run, runtimes, operating systems. So, Microsoft tries to meet customers where they are. So we'll tend to offer a lot of options. That translates on the delivery side into lots of support burden to work with lots of different providers for those operating systems and so on. More schedulers. Kubernetes has come along, so we now need to take containers a lot more seriously than we were before. So we're looking at, also interested to see Charlie Cloud and these other guys, and I'm going to get cut off on it. Biggest pain points for our users, porting and validation is a big one. So while we're introducing platforms at quite a pace, the ability of our customers to keep up with that is quite limited. So we're seeing some customers who can take 6 to 12 months of porting work. The porting these days is relatively trivial. It's the validation part, which can go on for months and months. So we're looking at, can we find solutions to help automate that? Are there AI tooling that we can bring to bear on those types of problems as well? So they're areas we're exploring. Gaps in the software stack, I think, I've mentioned it already, the lack of a common open source programming environment. So what we would like to have is a minimal environment where if I log into Microsoft or I log into any other hyperscale cloud provider, or I log into an on-prem HPC system, as an end user, I'll find my Fortran compiler, I'll find the common libraries that I'm interested in using with my application, and I can get up and running a lot quicker. Cloud vendors will tell you that those are, very frictionless processes. We can spin up infrastructure, in seconds and so on, but it's the work that happens after that to firm out the environment to get it running for your application that takes time. And that's the pain point that I think we would like to focus on as part of this community. Yep.
Thanks. All right. So next up is Dan. So here you go. Please try to be fast.
I'll talk fast. I don't know if I'll finish fast. Thanks, Todd. And thanks for the invitation. Great to be here. I'm Dan Stanzione. I am from TAC, but not TAC as in your technical advisory committee you were talking about this morning, but TAC is in the Texas Advanced Computing Center. And so I'm not going to belabor what TAC is. I think a lot of you have heard of us, but we're one of the larger university-based centers, mostly NSF funded, which may turn out to be a poor choice given the state of the government today. But the at least 30% of the NSF is left. But but we also do some providing for NIST, NASA, NIH, DARPA, DoD. Some of those still have some pieces remaining. We run a variety of systems. We have about 20,000 servers on the floor at any given time. Hopefully we'll be deploying 7,000, 8,000 more this year. A couple thousand GPUs, million CPU cores. GPUs growing faster at this point. But we support about 3,000 projects, maybe 40,000 active user accounts in any given year. Again, mostly, for the NSF sort of open science user communities. Much as Mike said, when you ask us about what our main application areas are, the answer is yes. I actually have measured on a couple of our machines that have been up, for a few years, and during their lifespan, a typical one of our bigger NSF clusters will run about 4,000 different codes, user binaries. Actually measured by checksums on the binaries, so there's a lot of versioning in there, but that does count things like apptainer as one, right? So if you count all the containers as one app, then there's 4,000 more. I would say that particularly with the newer GPU-based machines, obviously in academia like everywhere else, AI is exploding. Python's growing even faster than AI because all of the AI is in Python and then some. And although there's many issues to talk about today, I'm going to harp on that one. And the vast majority of our tickets and problems related to systems are caused by Python one way or another. In fact, there was because apparently when in funding crisis, my staff make new logos, but somebody was trying to figure out how to put the AI in TAC with this one, and there's now at least 75 AI-generated versions of this with various different blings that put the I inside the A inside of TAC there. As AI has sort of taken off for us largely. Problems that were issues 5 years ago that we've solved or at least significantly mitigated. I had to think about this because it does feel like one long continuum over the last 30 years of this. But I think containerization is an area where we've made a huge amount of progress. We had a talk on Apptainer this morning. We had a talk on Charlie Cloud this morning. Between Apptainer / Singularity and Charlie Cloud, those support is now standard on sort of every system we have. Most other places you go, you'll find them at the HPC centers. It's just not that hard to grab a container. Users are better at managing that sort of Docker to Apptainer recipe conversion to get things out. So, there's still a few holdouts where the fact that we can't run Docker in full user mode it gets to be a problem. But 5 years ago, this was an area where it's like, what about containers? And users would say containers like Tupperware. But now it seems to be a fairly standard thing we see a lot. So biggest software pain points, and again, just harp on this one. In a word, it's Python. In 3 words, it would be Python package managers. So pip, conda, miniconda, poetry. I think there's at least 2 more. We all see that, especially in the AI world right now. I used to complain about the state of the scientific software stack, and then I learned about the AI software stack, and now I think of the scientific software stack as a mature and stable and a well-built set of tools, as opposed to these, giant collections of 2,700 Python packages that work for about 4 days and then change. So, but yeah, there's super fast churn of stacks. So there's no way to have like a good module set to make people work very well. The package managers in Python are a classic example of the worst possible I/O you can do. There is Conda's ability to kill Lustre is fairly amazing and reliable. So it will kill Lustre every single time. There are so many workflows we've seen where it's like, oh yeah, the users created 400,000 files in 10,000 directories in 25 minutes. Most of those files were being written on each of 1,000 MPI tasks to the same path in the shared file system because there's a shared nothing assumption, assuming it was cloud and that there are no shared file systems. So it is the #1 failure mode for Lustre, which is why we've moved off Lustre for most of those machines at this point. But that is painful. So how can you help? If you haven't been listening, some help with Python would be nice. I think SPAC actually has many of the features that the Python package managers lacks, but I'm not sure another package manager in Python makes things worse or better. SPAC used to have problems finding like already installed dependencies, but that's gotten way better over the years, and it's always good to hear about the progress getting made there. But I'm not sure what the solution is there, but there's got to be a better way than what they're doing. Just to touch on maybe one or two more. If you've worked in Torch, it makes switching precision really easy, right? It's a parameter you can pass as to what precision to do your floating point at. Given where we're going in architectures, where FP64 is going to slowly disappear, not so slowly. I think by Rubin, it will be NVIDIA Rubin GPUs. It'll be almost all emulated. FP64, we're either going to do emulation or use lower precision functional units in another way. So it would be nice if it was as easy as it was in Torch to change things. And then lastly, maybe a little bit on portability. From what I see among the grad students, I think Cocos is the sweet spot for professional programmers between the ages of 34 and 52, roughly speaking, because they're the C++ people. And then if you're older than that, you do Fortran. And if you're younger than that, you're doing Python, which is the new Fortran. So I don't see a lot of, it's a smattering of codes that touch C++. Some of the big community codes, obviously, but a smattering that have Cocos versus the thousands that do Python. So I'll stop there.
Thanks. Yep. Okay, no, it's good. All right. Heidi, you're next.
I'm next. Great. I go after that? Wow. Nice.
Just go fast. It'll be good.
Oh, yes. Okay. And it... Yeah. All right. So what I'm going to do is talk about just a few things here. Instead of just enumerating through the questions, I'm going to do a little different. One of the things I wanted to tell you is what type of applications we run in the HPC space on AWS. So I thought I would just put a little bit of a glimpse up here for you, covering the different industries: healthcare, life sciences, energy, weather, climate, modeling and simulation, traditional things like CFD codes, molecular dynamics codes. All of those are very familiar to everyone here, hopefully. Also things like EDA workloads. So you can see what we have is we have a broad variety of the type of workloads that we run on our infrastructure. So now what I want to do is I want to talk a little bit about a couple of customer examples or a couple of code examples. The first thing is weather modeling. Is there going to be a shift to use AI? I don't actually know the answer to that question truly, but we are seeing some evidence of this and some exploration in this area. This is a specific example where we had a customer running hurricane simulations on CPUs. And we worked with them to use ForecastNet, the ML model from NVIDIA. It's the open model from NVIDIA. And they were able to switch from running about 3 hours, running a single simulation in about 3 hours, to running over 2,000 simulations in 10 hours. And so this opens the door for new types of exploration, new types of analysis from the weather perspective. So I just thought I would let you know that kind of thing is going on. It's out there. And so we're excited to be able to support users in this area. The other example that I wanted to talk to real quick is an example of a code that we have in-house that is open. It's used in our Center for Quantum Computing. We call it Palace. And in fact, I believe Cameron is there if you have any questions about Palace. He's the guy to talk to. What I wanted to talk to here is the importance of open software. Not only do we make Palace open, but we also use things like SPAC in order to build it. And it is built on MFEM, so it does use MFEM at its core. So we look for ways that we can use software that fits the purpose, just like we want our customers to be able to do so. So the biggest thing for me is, and the happiest thing is, to enable a customer, allow you to bring what you need to AWS and allow you to be able to get your work done. With that, thank you very much.
All right, thanks, Heidi. Okay, next up is Sarah. Sarah, I guess I can just advance the slides for you. Is that okay?
That would be great. Thank you so much. Yep. Yeah, thanks so much for having me. I apologize that I'm virtual. We are still under a pretty heavy travel restriction here at the NNSA. I'll go pretty quickly through this, just a little background on me as I just joined the NNSA in January of this year when all the excitement happened, the federal government. And I previously spent 19 years in the Army, kind of focused on test and evaluation and modeling simulation. I am the Federal Program Manager of the Computational Systems Software Environment Subprogram within the Advanced Simulation Computing Office of NNSA. Next slide, please. And then just a very high level, we are located within Department of Energy, National Nuclear Security Agency Administration, NNSA, and specifically our group focuses on the Stockpile Stewardship Program, which is an integrated technical program for maintaining the safety, security, and reliability of the U.S. nuclear stockpile. The ASC office, Advanced Simulation and Computing, is a cornerstone of the Stockpile Stewardship Program, and we provide simulation capabilities and computational resources to support the annual stockpile assessment and certification process, study advanced nuclear weapons design and manufacturing process, analyze accident scenarios, weapons aging, and provide tools to enable stockpile life extension programs. I was not going to read this whole slide unless there's questions in the audience. So next slide, we'll get to the interesting stuff. And then I just did a high level review the questions. So right now, NNSA primarily leverages HPC for scientific simulation and analysis. There's a small amount of AI that is leveraged. And in the future, while we do anticipate greater use of AI, due to kind of, I think, restraints with security, we will never fully replace HPC in the NNSA federal laboratories. At least that's not what we anticipate. At the moment, what we're seeing is that there's not enough modularity. You can't mix and match different software stacks, that you can't do different components. And the testing of various components is lacking. Therefore, the software stacks become kind of brittle. Another issue that we're, have been seeing is that, there's a lot of unique custom applications of the stacks and not a standard way to stand it up. And then what we're looking for from HPSF is, to bring the community together, to unify that vision within the community. And we would like to see, within our portfolio, a reduction in duplication of software and software stacks. And also help with testing the interactions between all the different software programs to hopefully increase some of that modularity. And I believe that's my last slide.
Okay, thanks. All right, so next up is Jayesh from ULIC. So here you go.
Thank you. So I am a research scientist at ULIC, and there I have a couple of different roles. But in the past few months, I've been working on getting the continuous benchmarking going for the Jupiter, which is our upcoming exascale supercomputer. So the main application areas of JSC, as you see, are on the left. You see, so this is based on the compute time applications, and we ask them questions what they're doing, and sometimes you also see what they're doing because they ask us for help or something. And you see that we have a very scientific application base, and a lot of these scientific applications, then if you see on the right side, they are using AI in some form or another. Already 41%, either as a already existing workflow or something. I think the computer science is pure AI. Some of it is pure AI at least. So in future, what we see from our compute time applications and what we see in our early access programs is we have a lot of traditional HPC applications, but a lot of them are now starting to use AI in their workflows as well, machine learning stuff. And then we have additional AI applications which are going to come through the upcoming Jupyter AI Factory initiative. So what kind of problems do we have and what kind of solutions? What kind of problems do we have and what kind of solutions do we want? So one of the big problems is very similar to a lot of people, that is a very good stack. And so you can see a full stack of a supercomputer here, and then you start with the hardware at the bottom and applications at the top. And you can see the responsibilities of different groups of people. So vendors have up to compilers sometimes, and then stack maintainers, which can also be sysadmins, or community package managers. They have the other parts there, and then users are doing applications or scientific libraries mostly. Sometimes also tools, but mostly scientific libraries and applications. And the biggest problem is, of course, to deploy, maintain and deploy this stack in a good manner. And for that, currently, we started using continuous integration and continuous deployment and auxiliary clusters, which maintain the same environment as our deployment machines. And then the community support became very important, because when you have this kind of an overlap, you need information to go from one stage to another very quickly. And for this, if you have a good community, then the information flow is faster. And so this you like. And then the uniformity-ish of the workflow between platforms, because it's never truly uniform. And at JSC, what we have is all the different supercomputers that we have. They are all connected using a very similar stack. So the user workflow for loading the packages is extremely similar. So they don't have, and this allows them to test on different machines very quickly. And what we are trying to do is we are trying to have more user drivable dependency management, because if you want to provide just all the stacks that are possible, then this is just not possible. And so users will always have some different system configuration. So this is one of the problems that we have. The second problem that we have is, historically, academic software is particularly challenging for the quality. Software is generally written for science. It's not written for utility, because that's how the funding works. It's mostly for publications, not for infrastructure. And recognitions then also you get for publications versus software, right? That is kind of the organizational part, but a more technical part is that the development is very diffuse. So you might have different organizations with different timelines, with different employment contracts, all of them collaborating on a software, and now this becomes difficult to handle, difficult to manage. And a lot of software practices sometimes feel like they are developed more for very core industrial purposes, where you have one team or multiple teams, and then when you want to balance this becomes hard. Exploding hardware complexity, as people have talked about, and implementation effort as a quantifiable work in research. And for this, what we did is we had research software engineering, which is an initiative, and which a lot of people have done, and this really helps. So this is helping us do the visibility for research everywhere. And so what are the gaps in HPC stack? So a lot of people have already talked about it, so I would not get much into it. But I would say that the containerization, there is a risk with it, because you don't see what's happening. And so there's a lot of duplicated work between teams, which can technically, and there's also a lot of ossification, because once you have containerization, then people don't try to move to new dependencies. And then we need incentives for applications to be more at head-ish. And then what I feel is the benchmark workflow specifications look very deceptively different. So they are not that different actually, but they look deceptively different because we think of resources in a very different way. But whether it's a cloud or whether it's a supercomputer, you still have to deal with localities some way. And I think there is a lot of opportunity to get stuff done in a very similar manner there, and we can reuse a lot of different things there. And then too much hardware variety to be tested by a single entity. And then I think it's very important to collaborate on stack support for different hardware, so that different people can test different things. And then we can collaborate on making sure that the stack is validated and trusted everywhere. Thanks.
All right, thanks. Okay, Noor, you have one slide, I think.
Yeah.
And
So,
I put your other answers on the other slide if you want.
okay, thanks. So I remember. So nice to meet you. My name is Nufadel. I'm unit head of scientific computing unit at CSCS. So why I put only one slide? Because in the past and the current present and the future for CSCS is Alps, is our machine we designed in the last 5 years. We focus on designing a machine based on our use case. First is weather and climate. The biggest user of CSCS resources is Meteo Swiss. So we designed with them a machine that can scale with their workload. And in the past was Cosmo that we ported to GPUs and was used in production since 2016. And now we are porting Icon, so the new software which has actually mainly developed in Germany, but we have our version, toward being without OpenACC. So in the first step in the past was to use OpenACC. Nowadays we are basically developing a code called DACE, which is basically automatic generation of software, specific software for each specific platform. Alps has currently 2 architectures. So one is AMD MI300 and the Grasshopper. And in this way, then we tackle the performance portability. This is our attempt for the next 5 years for the main application that we have, so Icon. And we are closely developing this with Meteo Swiss. But then, in order to help the scientific community, Swiss scientific community, in the past and also now, we have a specific project where we embed developers in the research team in order to, in the past, port the code to GPUs. We used in the past Cocos. In several projects, we will still use Cocos because depends on the community. Certain community, they appreciate a lot Cocos, other a bit less. So we try to adapt the technical solution based on each community. By the way, in the audience, there is a few developers of the past projects. Then, when we design Alps, actually, we haven't used only this use case, but we already foreseen the AI could be, the next big thing. And actually, together with NVIDIA, we decided to use as a first Grasshopper in 2020. And we think right now we give 50-50% to classical HPC and AI. Probably in the next 3-4 years, we will raise the part of AI or ScienceML to 80%. Then let me check because I don't remember anymore. Okay. In the past, the main issue was definitely porting to GPUs. Nowadays, the idea is to have a software that can be readable for the user, so for the domain science, but at the same time, keep the performance portability. Then actually, this is not only the main topic for us, it's also to embrace new communities. One we already said is AI, and the main pain point is currently, I would say, the collective communication libraries. So Nickel, Recall, all these communication library that creates a lot of pain, at least at CSCS, because they are fast, but they are very fragile. So anything we change in the system, I see even, I don't know, I leave a lot of the storage or the driver, this library breaks down. So I would see as a hope and HPC Software Foundation also have, this attempt to have more, standardization on this side, especially for AI community, because it's crucial to scale up for AI. And then other communities like confidential computing. So this machine has been designed in order to have segregated part of the machine, so and encrypted in a network. So the idea is to carve out single parts of the resources and give to specific universities. And for this reason, we are inside Ochami, and we will actually developing in Ochami, so inside the HPC Software Foundation, because our idea is the next, not 5 years, I hope earlier, next 3 years, to remove CSM, so the management plane of HPE, and replace with Ochami. And I think, yeah. I think that's all. I finished the time.
All right, thanks. Thank you. Okay, Doug is next.
I'm Doug. I work at Google Cloud. I'm a software engineer. I have worked in HPC for a while. I'll try to be quick. I don't really need to repeat things that agree with what everybody else said. At Google Cloud, you can imagine we have a lot of different types of customers that cover a wide range of applications. It's also hard for us to know exactly what people do if we're not involved in a POC, like was said earlier in clouds. So a lot of things. I don't think there's anything else on here that's worth saying. Similarly, it's kind of hard to gauge how much work is going to transfer from HPC to AI over the next few years. Interestingly, also, like the other two clouds that have discussed this, I'm going to point out weather and climate, which both of them talked about as well. There are operational weather models that use AI to forecast instead, and you can similarly run lots of forecasts in a short amount of time compared to traditional HPC workloads that do weather forecasting. However, the weather forecasting models train them as well, so you have to build up the training data set to be able to use the AI model to forecast. I am giving a little bit of my own perspective of what I see for our users. I think one of the biggest pain points for customers, for our customers, is reproducing our performance when we run it. And it's not really that like it's hard to get the same performance. It's more that taking a workflow that's foreign, that maybe like I come up with, and porting it into the customer's already well-defined workflow is a non-trivial effort, which is kind of like saying validating performance is hard in a POC when you have to translate stuff. I think that is kind of difficult for people, and some work could be done to make that nicer. Gaps in the HPC software stack and how it could change to deal with new application areas in AI. One of the big things that's been a problem for a while has been a lack of standardization in accelerated compute frameworks. We have lots of options, but there isn't a standard, which is why every accelerator has its own language, syntax, framework that you use to write on it. That makes it kind of hard, and then you need layers like Cocos, which does a really good job of this, but you need them to layer on top to get any kind of performance portability. It's also worse when you consider the Python problem that was mentioned earlier and how that kind of disagrees with what a lot of the traditional HPC software stack has been for a long time. How could HPSF help? I think first, I complained about standardization. You could push standardization. I think that Cocos being involved in the C++ standard is doing a really good job of this, but all aspects of this are important. I don't know how much forcing vendors to participate in these standardization efforts is possible, but that would be really useful. I think that I haven't gotten a sense this morning from the participating projects in HPSF that AI and ML are an interesting market to collaborate with. They're a really big source of effort for clouds nowadays, and it would be kind of nice to have some collaboration between those communities. The software stacks are different and they don't play nicely together all the time, so it would be good to work together and figure out ways to help that in the future. And then I talk about containers as well and package managers. That's all I have.
Okay, let's thank our panelists. All right. So if you have questions, you can go here. I guess I would like to have this up for a second and then bring Sarah back because she is a panelist and we don't want to forget that. So who has not gone here yet? And okay, I'm going to give everyone like a minute to write this down and to go to the site and to enter the questions, and then we're gonna go on with the we're gonna switch to Sarah. So already people have asked some questions. There are the most. I'm going to start with the most upvoted question. So because we're going by votes and everyone can log in and star the questions. So how do we ensure an HPC talent pipeline in the face of higher salaries in the AI industry and AI tools that interfere with the traditional process by which junior developers have become senior developers? I think that just boils down to what are ways that we can ensure an HPC talent pipeline? Who wants to take that one first? Okay.
Yeah, the university guy has to talk about pipeline stuff. So yeah, always. So it is obviously a huge challenge, right? I mean, but for us, it was always a challenge losing people to the people sitting on my right and left and the cloud vendors. Yeah, but the AI just means instead of leaving for twice their salary, they leave for triple. But I think the same things matter, right? So first of all, I'm not bringing in a lot of AI trained CS PhDs to do AI. I'm bringing in a lot of physics and chemistry PhDs to do AI, who find it fascinating and have plenty of computational and, more importantly, numerical skills to do that kind of stuff. I don't expect them to stay forever. We find that we get new grads who are interested in the work, and we get sort of late career people coming back who would like to do interesting work, having worked in industry for quite a while on, making sure the blue screen of death looks perfect. So, and I, got probably 10 of those at the moment. I do think what works in our favor here is that whether it's, other than the number of bits, there's just not that much difference in the workflows between AI and HPC at the moment, right? You still have to run large interconnects. You're still trying to figure out large file systems and high performance IO. So the skill sets are going to be very similar. And in some sense, I think it's drawing a lot more people into the field than there would be. And we just have to, sell the mission as always. But, tens of thousands more people working in the system side of large-scale AI is only going to help the size and skill, I think, of the HPC workforce. So,
anybody else want to take that one? Yeah.
Just say we're hiring.
Okay, Sarah, did you want to answer that one at all?
Yeah, just our experience is very similar. We have the ability to pull in kind of college grads, young interns. Government offers a lot of educational benefits, but typically once they get those perks, they're usually gone in about 2 or 3 years. So the question is, how much work can you get out of them once they're trained up in AI before they depart? It's a difficult problem.
Okay, anybody else, or should we move to? Okay. All right. So are you marking the answered questions, Christian? Or let me see. Okay. All right. The next question is like a little bit not what the panel's about, but let's try it. Thoughts on Rust? Should humans be trusted to manage memory, or will code generating tools solve this for every language? I guess we can boil it down to Rust in HPC. Do you see it happening? And anyone want to take that one? I think we may have. Yeah. Oh, Dan's going to take it. Okay, awesome.
You'll find that in silence, I'm going to answer every question that's thrown out there, because I may not be right, but I'm still going to answer. So, so in short, no, I don't see a lot of Rust adoption coming. I am terrified by the notion of it being auto-generated code for a lot of this, because I think we're about to see a world where there's just an onslaught of a huge amount of automatically generated software, all of which works well like 94% of the time or something around there, and has 5 or 6% of the cases where there are bugs that are absolutely undebuggable, other than going back to the AI that wrote it and saying, please start over and don't put this bug in. And then you get another 5 or 6% of edge cases that will be bugs. So that is somewhat terrifying, just in quality of software in general, not just in memory management, but I think again, Rust, so in my world, 90% of our users are graduate students, right? And 90% of those aren't CS grad students. They're like geology grad students writing seismic codes, right? So, the odds of them worrying terribly much about memory management, unless it's the thing that's standing between them and graduation and doing the extra work for it, kind of low. So I think that's going to have to come, would the labs do it? Maybe. Yeah, I think anything that sort of raises the bar is a tough sell right now.
Anyone else? Yeah, go for it.
So I don't know. So it's difficult to predict trust, but as the talent pipelines is C++ is becoming a little bit unpopular among young people because it's getting more and more difficult to program correctly somehow. And but the thing is, even though with Rust you can program and get correct results, people don't want to move to it. They would rather move to Python with a slightly slower performance. So that's the difficulty.
Fairness, C++ isn't harder. They just don't want to.
So for CSES, we don't have anything in Rust, but we are basically investing like an incubator. So basically, every colleague at CSCS has 15% of his time to learn new things, and we are investing in AI and Rust. And currently, we are evaluating a few projects, potentially the usage of Rust.
Anything on that one, Sarah? Nope. Okay. I'll answer this question a little bit. I'll get out of line. I guess I'd say we're interested in Rust because it's got a lot of uptake in the Python ecosystem, at least for tooling. And so like we could probably speed up a lot of horrible things about SPAC by getting some Rust in the core. And so that's sort of appealing and especially because other package managers like UV is one of the newer ones is going in that direction. For computational science, like it's an interesting time to be alive because C++ is getting more adoption in computational science because I mean it is a really good language for accelerated computing, and a lot of the frameworks for lower level accelerators are in C++. Rust is not nearly as mature in that area, and so it's going to be a while before I think Rust builds out a computational stack. But it'll be interesting to see what happens when it does. So I mean I think you're and it's also interesting because at least one of our administrations encouraged folks to use memory safe languages. And people, there was a lot of interest in Rust around that. And C++ was sort of declared a legacy language just as it's catching on in computational science. So I don't know. I think it's going to be a while before there's a migration, but I think it's an interesting direction. So, all right. The next question in here, I can mark that one answered. What's that? Oh, you are? Okay. Well, I still see it on here. Okay. We're just not synced. I don't know. We need to work on this app. All right. What influence, if any, can HPSF apply to steer hardware vendors to build required FP64 optimized hardware? Or should HPSF focus on proving mixed precision strategies? Yes.
We will have tomorrow a panel where this will be definitely a topic. From a hardware people.
Okay. Yeah, I think yeah. So we'll hear more about this tomorrow, but yes, go ahead.
Todd told me to say none, but I think it's kind of hard for HPSF in general to do this unless they come up with like a benchmark suite that everybody uses for RFPs forever. But I could imagine that the benchmark working group participates in putting together evaluations of FP64 machines that then make vendors look good or bad. I don't think that's a good idea for HPSF to do. I don't think you want to make vendors look bad, but that's an option.
Any other answers? Dan's going to answer.
Yeah, why not? Just shut me up whenever you're ready, Todd. But the I don't think the benchmarks is necessarily about making vendors look bad, right? It's an effort to try and figure out if their hardware works on our problems, for the most part, and to do some sort of fair comparison. And I think the precision thing, if you haven't tracked this, right, like if you look at like int8 performance to FP64 performance, right, I think it's something like 20-to-1 in Hopper. It's something like 100-to-1 in Blackwell, and something like 2,000-to-1 in Rubin. So, and you get to the point where, if I can write a good FP64 emulator that takes 220 instructions to do one FP64 application, it still might be 8 times faster on a Rubin than doing native FP64, and 8 times more energy efficient as well. So, we're going to have to figure out how to address this. I think there's a, sort of burgeoning space of mixed precision algorithms, right? Where can we scientifically validly use 32-bit or 16-bit, outside of neural nets. But these emulation libraries are going to be crucially important as well. So, it's sort of not to trash the vendors, but it's the hardware they're getting because it's where the market, it's the hardware we're going to get because it's where the market's going. So we just, we got to find benchmarks to make it work.
So I just wanted to say another thing too. I consider this an opportunity and an interesting time. So we haven't really had the situation in recent times where FP64 performance is under question or under some sort of worry. And for the research and the scientific community, there's so many things that we can do separate from emulation. Have we bothered to go look through our codes to say what actually does need 64-bit? Have we bothered to say, just like with GPUs, we figure out how to move data back and forth efficiently? Can we figure out how to compute at different precision levels efficiently? So I'd like to, I'm interested in how this is going to play out. I'm very curious to see what's going to happen, whether we have any way to influence vendors. I think Dan is right. I think vendors will go where they're, where it's most effective for them, right? And I think the scientific and research community has an opportunity and to think outside the box on how we can take advantage of this new world.
Okay, we've got, let's see. The next most voted question is for Sarah. So NNSA, how much does broad applicability of projects outside the NNSA factor into internal project funding decisions?
That's a great question. I would say, so I've been there 4 months. I haven't fully gone through a year cycle process with the PB budget planning. But I would say, everything's in a 2 to 3 year cycle, so things do have to be proposed early enough. I'd say with the current climate, I think there is a look for things to align very directly to NNSA mission, and specifically for us, the defense programs. So I'm sorry if I didn't quite answer your question. I'm going to phone a friend and say, Todd, what is your perspective since you've been here longer than me?
Okay, I guess I get to answer this one. So we have to justify everything in an NSA by applicability to the mission for sure. But oftentimes the best thing to do for the mission is to build something that's usable outside the mission area. And if we get adoption for products, you saw the chart that Greg showed earlier for SPAC, and you've seen how the adoption for Cocos has helped build out the product. Those things benefit NNSA. And so if we can build things that are real, things that get used by people, and things that ultimately become the most robust they can be through community participation, then that's ultimately good for the mission. And so we just have to balance those two things and make sure that we're clearly justifying things as actually beneficial for the mission. Because we can't say that we're working for Amazon or Microsoft or for the AI industry. We have to say that we're working for the Stockpile Stewardship Program or for a modernization program or something like that. But I think there's very clear justifications we can make for open source. And in fact, Ask and Oscar, the two major supercomputing programs within DOE, have a public document that says that they prefer things to be done open source unless it's necessary not to. And so it's something that these organizations have supported for a long time, and we get a lot out of open source. So I wouldn't take mission justification as fundamentally opposed to broad applicability. Okay. All right. So let's see. All right. Panel, what do you think post-GPU HPC looks like? That's how the question's worded. So who wants to take that one? I think it's Dan. Everyone's yeah. Okay.
Volunteer. All right. It's just awkward if you don't volunteer. So yeah. So post GPU, that'd be good. Post GPU HPC. So well, first of all, are we going to have a post NVIDIA HPC ever? At this point, the other GPU manufacturers are probably not helping in that regard. So I think that the near-term future for us, right, is figuring out how to exploit AI hardware with a lot of things Heidi just talked about, right? Using the low precision circuitry as best we can, right? I think that's the inevitable near term. I think there's two promising directions in the longer term, right? And we do have this opportunity to do more exploration in the hardware space because essentially of the end of Dennard scaling, end of Moore's law, there's only so many atoms left that we can shrink things across. So it means that, if you have a cool architectural idea, you're not going to get swamped in 2 years by the fact that the mainline processors have just surpassed your performance, which means we can explore, but at the same time, the community and, you mentioned the time for validation and science codes are just as bad as the commercial codes, except maybe the validation cycle's like 2 decades on some of them. But the programming model changes are hard to push, right? So hardware that does something radically different in programming, probably doomed. So what can we do? One is, the chiplet concept and sort of semi-custom chips, right? Custom HPC chips, not going to happen. But being able to say, I want more floating point units. I want more cores of this kind, right? I want more large cores. I want more energy, and just changing the mix from sort of a library of parts and getting the vendors to do, more memory bandwidth per core or scatter gather accelerators or something like that. I think that has real promise of being a sort of next gen, right? This is a number of years out, right? But of working, there will inevitably be pressure for us to figure out how quantum works. And we will run our quantum computers from our fusion reactors at some future date, roughly the same. And so, energy of the future now and forever. So I'm not sure we'll get there with quantum in the very short term, but quantum is the other accelerator that you can't not pay attention to at this point. But but I think semi-custom is probably the first post-GPU thing we'll probably look at.
Yeah, I would say for sure in the next 5 years, probably we know that there is this European processor initiative, but definitely the next technology for sure should consider to consume much less because our, at least our facility reached the maximum of the energy consumption. So definitely the technology should have 1 or 2 order of magnitude less of energy consumption. And you mentioned quantum computing. I think also we should consider in the future other technology like neuromorphic and optical computing, but we are far away from saying that will be successful. I mean, we will see in 5-10 years.
Sarah, do you want to answer that one? Nope. Okay. All right. Let's see. So, what do we got? So someone's asking, TAC mentioned that Python package managers kill Luster. Does Python at runtime also kill Luster?
You never make it to runtime after the package manager finishes killing the file system, so I don't really know. But the yeah, so I have seen less problems with Python at runtime, other than the usual. It's just not necessarily as efficient, depending on. But you can write bad code in any language. So no, I've seen less problems with that. It seems like package management is the Python specific downfall. There are a bunch of other applications that do hideous things to IO. Again, our favorite one is we killed the guy after 3 days. He was creating 10 million directories a day. The good news about that is we found out we can create 10 million directories a day, which I had no idea we could do that many on the Frontera file system. But at 30 million, we cut him off, deleted all his files, and he still had 80 gig on the metadata server for the 30 million directory entries that he had. So you can do, and that was fairly popular CFD code that maybe the Navy supports. So you can figure it out from there. But so there's bad IO all over the place, but the Python package manager seemed to be a special case. After that, Python, you have the same IO problems you have on everything else. There's nothing special about it that I know of. Yeah.
No.
Okay. All right. Okay. Let's see. Oh, question for Microsoft. When hunting, so this is a good one for the panel too. When hunting for programming environments, is it the lack of open source free programming environment? Is the lack of open source free programming environments the problem, or any PE at all? What's wrong with Cray PE? So you can answer it with or without the last part, but I think it's more interesting if you answer it with the last part. All right.
Okay. Yeah, so we should be honest.
Yeah. So I anticipated that question, which is why I mentioned that we run Cray EX in Azure. So we do run the Cray PE. The problem is it doesn't run on Azure, right? So if I want to run applications on any of my other infrastructure than the HPE hardware that I have, I can't do that. So that's why we're looking outside the box. With SPAC, we started using SPAC about 5 years ago. I have my own open source programming environment. Part of the reason to be is just to talk to other people and see, what are you all doing? It seems like everybody has their own open source programming environment. So my question is that ripe for some sort of standardization?
Yeah, you can. Hey, I've talked at least once. So programming environments have been in my past career. So I'll maybe make a comment. One of the things that I see is it's very hard for us to settle on a single version of a programming environment. Applications are developed typically through language chosen. The language of choice for an application has meaning. It could be the language that the developer is most comfortable with. It could be the language that is the best fit for the problem being solved. And then once you've got an application with a certain language, you go hunting, you've been building it with a particular programming language or a programming model, a specific compiler and set of runtimes. And there is no real reason to just switch, use a different programming environment for that particular code. Now you imagine a whole bunch of codes and everybody has done that same thing. And it's pretty hard to hone in on a single compiler, a single set of libraries, a single set of, math and kernel libraries, different components, as well as debuggers and profilers. You can see we have a wealth, although that maybe compilers are shrinking, I don't know. But I don't think it's in that having that diversity creates questions and it creates innovation. What I just don't want to see is I don't want to see, for example, compilers just go away. And I don't want to see people not learning how to work on compilers from the workforce perspective. So generating a single solution to me seems like it's not really, I speaking personally, don't think that is the way to go.
Yeah, I would. We created our user environment on Alps, which is based on SPAC, and this gives us a lot of flexibility, much more than Cray PE, and also it's easier to debug and fix. And we are very open, and we are really, we want to invest in HPC Software Foundation for standardization. I think having diversity is crucial. And I would try to have some, instead of having one user environment, having some standards so we can, have an interoperable way interacting with the other centers. One thing only, sorry, we are really focused on having, as much as we can, the entire stack open source, because in this way we can fix easily in a fast way, and instead of trying to, poke in the vendor, in this case HP, but in general it's always the same everywhere, to find where is the error, how to solve it, and so on.
Doug, you want to add? Sorry. That's okay. I think one thing that I've noticed that maybe complicates having a standard programming environment is that a lot of our customers tend to use ISV codes, which don't necessarily live well in something like SPAC. Like SPAC doesn't have install for random ISV apps that they use. They also tend to have similar validation issues that have been mentioned on the panel already, where they are not very keen on jumping from one version of some ISV app to a next version because they're afraid it's going to change their software and they don't want to invest in revalidating all of their simulations to be able to do that. I think that that is a place that would be cool to have standardization, having like open source tool chains and software stacks mesh nicely with ISV ones as well.
And Sarah, I think you might want to take this question since you have some NNSA software stack efforts coming up here. So I'll give you a chance.
Yeah, I'll make mine kind of brief. But yeah, we are looking towards not necessarily standardization, but I kind of said it in the beginning. Like modularity. We're looking for some level of modularity and interoperability, so that we can have at least maybe not a standardized software stack. But at least a software stack framework and diagram where pieces can be moved in and out. And so we're looking at doing that. What does it look like today, and then also what does it look like 5 years from now, as things continue to evolve and it becomes harder to continue to get more processing power out of HPC GPUs and leveraging other avenues. Thank you.
All right, thanks. Okay, the next question is, let me squint at this one. I wrote a lot. We write large applications with hundreds of contributors that have to run on commodity hardware as well as taking advantage of HPC systems. What suggestions do you have to make our developers' tasks as easy as possible? I'm going to start with Jayesh.
I think the biggest thing you can do is have same workflows on both, even if the implementation details are different. And I mean, Spec does this well. So, for example, if someone has to use a different way of installing dependencies on every different system, then this is the biggest slowdown I've seen. Getting the first run to run is the biggest time consuming. Once that is done, then everything else works out. So I would say we focus on that first and then the rest.
Yeah, I don't know if I have anything else to add to that. I think I agree.
You actually mentioned this problem with like taking a foreign workflow and handing it off to somebody else. Like, do you want to? Sure.
I mean, I think for this specific question, you have to kind of define what you mean by make it easy for the users. Is it developers or users?
Developers.
Okay, so specifically you want to make it easier for people to add lines to code. So then it depends on what they're trying to do. Are they trying to optimize or add features, add physics?
Well, here, let me add, maybe I can make the question more concise. They're asking about commodity versus HPC. How do you make your code work across both effectively? And so they're saying, how do you solve those pain points for a code that has to run both on supercomputers and on commodity hardware or maybe clouds?
How do you make it easier for people to add changes that work both on commodity and specialized hardware? I mean, I think you make it easier to deploy the software stack, like was said earlier. I feel like the thing I mentioned earlier in my answers was taking proprietary workflows that different industrial companies put together themselves and port something like an open source workflow into that. And that is something that they're not really keen to do. I've had success by telling them, like, these are the only instructions I'm giving you on how to do it. And then that's how they do it, because they have to run the experiments and get the best performance they can. And then when they try to like port it, it just doesn't work. They can't get the same performance. So that's the path that I've done so far.
I'll add one more thing now. No, it's not a rebuttal. No. So being able to run between commodity and supercomputing infrastructure, it depends on what your goal is. If you want to be able to have the ease of use to just be able to run between platforms, if you think about that, that's one of the things that ISVs have to do. They have to be able to run across a wide variety of platforms in order to have their users be able to run, on the different platforms that they choose to run on. So for that, ISVs are already doing this. There's different things you can do. You could end up coding to the lowest denominator, and I'm not saying that as a negative thing. I'm saying as what is the thing that's common across all of the infrastructure that you want to be able to run on. And then you can take the approach that when it's important, then you tune. Then you add components in for the performance aspect. But it really depends on your goal. I mean, if you just want something that requires no changes and it doesn't matter what the performance is as long as it executes, that's going to be a very different solution and types of changes to your code than if you want something to run well on a variety. And so I guess I would hope that maybe there's some ISVs that will join us and not here today necessarily. I don't know if there is anyone, but it'd be great to get some input from them.
Okay, for this next question, I'm not going to lead the answer, but I will remind the panel that they're free to reject the premise of a question. All right. So what's the number one thing we can do to prepare our codes to run on cloud other than stop using MPI?
Heidi wants you to say.
What's the number one thing we can do to prepare our codes to run on cloud other than stop using MPI? Reading the question. Yeah.
I'm going to reject the premise of the question. I mean, I use MPI on cloud all the time. I don't think that has anything to do with it. I feel like I've been able to take apps that I used to run in on-prem HPC environments and run them on the cloud pretty easily. And I think this is true for a wide range of apps, whether it's HPC, AI, or ML.
Add one thing? Yeah. No, I won't talk about Python this time. So I had 5 minutes. You got to pick a topic. So, there just isn't, as Doug just said, right? There's not that huge difference, right, in the sort of exposure to, Linux versions, libraries, fabrics, any of that stuff at this point, right? It's pretty easy to write something that will run in multiple places. The biggest barrier to like moving stuff between HPC and cloud tends to be things like data locality, right? Is that people constantly ask us, why don't we just burst to the cloud? I'm like, because I have 70 petabytes of shared file system attached to there. And I have no idea which slice of it the user's going to talk to, but if you'd like to migrate all 70 petabytes, feel free. 7 months later, they'll come back. I just did one with a, cloud software vendor startup where it's like, oh, it's easy. You will be bursting in 2 weeks, and gave them about 1.5 years before they could learn the lesson that we already knew. Where 18 months later, after working on it constantly, they just give up, right? It's not the code that is typically the barrier, right? It is the billing model, where you can get allocations. Can you scale up? What's the max runtime? Where is the data locality? But yeah, you can run an MPI code, written in C++, Fortran, even Python, pretty portably, as long as you stay away from non-portable libraries and vendor-specific services.
Yeah, so one of the things that distinguish kind of cloud from supercomputing is the network, which is you have kind of a guaranteed latency between nodes in supercomputers, which you don't have in cloud. And so if you want to get the similar performance on your algorithm, which requires that kind of communication performance, then if you don't use MPI, you are going to recreate something which is very similar, which is essentially the same deterministic thing. So,
if I may, just one quick thing about you. Microsoft is the largest InfiniBand customer in the world, and we're tiny compared to them, right? We used to be like a top 10 InfiniBand customer when they'd roll out a fabric. I have hundreds of miles of InfiniBand cable. Was it 2024 where Microsoft installed 29,000 miles of InfiniBand cable, right? They're far and away the biggest consumer. I mean, yes, if you go across data centers, you're going to see a huge variation, but rack to rack, you can get 1,000 nodes and have uniform latency there too. So, yeah, Mike.
Thanks. Yeah, so agree with everything everyone said. I think the one bit we missed was around I/O. I think I/O is a challenge. So if you are thinking about moving workloads to the cloud, data gravity is an issue. You might want to rethink how you do I/O. I hate saying that. I would like to give you the exact same type of technology that you have on-prem, just magically appears as a file system underneath your compute. So, we can do that, but it's not the most efficient way of doing that. So if you can rethink the way you do I/O, modernize it, look at maybe using cloud APIs, address blob storage. I'm sure the same is true of the other storage vendors. Object storage is extremely fast. You can get multiple terabits per second of throughput from your compute directly into blob storage. You can put a file system in the way. You can put an all-flash file system in the way. You can use NVMe drives in the compute nodes, depending on what type of instance you're using. There's lots of different options. So just think through carefully what are your options rather than just assuming just lump a petabyte of data over and that's the most efficient way to go.
Heidi, one more addendum from...
I just want to add on to that just a little bit. Again, there's opportunity. We're used to file-based POSIX, file-based file systems in HPC, and object storage gives you some pretty interesting ways to look at data and to run through data, analyze data, and so it gives you a new opportunity to view your data differently or to maybe be able to process it more quickly. So again, other options is always good, I think, because we may find something really cool that we can use next.
Okay. All right. I've been trying to avoid this question. Yeah, no, it's okay. I'm going to go with the audience. I think the votes are, I gotta stick with the votes because it's a democratic process, but let's see. I mean, not that we care about this. All right. It's right. It's often stated that cloud is expensive to replace your on-premises HPC systems. That's true if you try to replicate a system. What about if you price the actual workload and not the system? Can you say anything about dollars per unit of science for on-prem versus cloud?
I'm not going to talk about dollars per unit of science because I think that depends on the workload and how fast you need it done. But I think that cloud offers a wide range of pricing models that make it more or less affordable when compared to on-prem systems. If you don't need your science today or tomorrow, it's a lot easier to come up with cost-effective solutions that are more enticing than trying to procure an entire system yourself. And it's a lot easier to get a system tomorrow that you don't have today in the cloud than it is to go through a full RFP just to get a system.
Yeah. All of what Doug says is true. Our cost advantage in, attack versus clouds is because we can, batch fill the systems and be full 24/7, right? If we couldn't be full 24/7, and the thing the users hate the most is the wait time associated with that, right? Then we wouldn't be more cost effective, right? So, there is certainly a trade-off, right? And people are like, well, I want interactive speed like the cloud. I'm like, well, you're going to pay us as much as you're going to pay the cloud at that point because I have to have servers just waiting for you when you're ready. So you get to buy those. So I mean, if your workload is, somewhat bursty and uneven, find the provider that gives you the best deal. If your workload is, I got to compute this stuff constantly 24/7 and it never stops, then the math changes a little bit.
All right. I had one in here. Yes. What's that? Oh, no, I'm saving that one for last. I know it has 54 votes, but it was, yeah, I guess we got 8 minutes. I wanted to do one more question and I'm doing that one because I think it's a good last question. So I didn't miss it. I see it. Yeah. Okay. I'm gonna pick one down here that, yeah. What role do language standards committees have to play in portability? I don't. Jayesh says he's going to answer it. We have experts. You want to get on stage, Christian?
I don't have a general answer, but I have a very specific answer. So I think sometimes it's a very big role. And an example of this is in C++, we have the random header. And the behavior is, the behavior for some pseudo-random generators is well defined. But when it comes to generating the distributions of randomness, it's left implementation dependent. And so you cannot use the standard randomness to reproduce your experiments on different system. And this is kind of the place where the language committees are really important.
So I guess I'll. So I came from the MPI world and was part of the MPI forum for a long time ago, MPI 2. So that was quite a while ago. And we thought about this, so I'm going to answer it a little bit differently. We wanted to support different languages. If I were a language committee, I think it would be in my best interest to make it reasonably easy to be able to move between my language and another. And the reason is I don't want to create roadblocks so that my language is not used. So I don't want to create barriers or walls so my language isn't used from that particular committee. The same goes for MPI and the different implementations, and also being able to support whether you're supporting C, C++, or Fortran bindings, for example. And in those days, we worried about you want to be able to support users where they're running and how they're running their codes, how to best run their codes. And if you create a language that's too difficult to be able to use with other things, then it's not going to get as heavily used. My opinion, personally.
I'll throw a quick opinion on there. I don't know how to solve this because of the way language committees work or library standard committees. I have people on the OpenMP review, architecture review board, but they need to be more nimble, right? If you look at what's the most popular accelerator library in the universe, CUDA, there is no language standard committee. What's the upcoming language? Python. I don't think there's a language standard committee there either. So, you're going to have to find a way to be more nimble or they're going to become obsolete. Let the AIs decide.
All right, Sarah, any comments on that one? Nope. Okay. All right, I guess I'll say interop is huge. I agree with Heidi. Like making sure your language works with other languages is a great way to ensure adoption, and it's where most of the language committees fall over because they're very focused on their language. It's also where most of the Python package management tooling falls over. So it makes it really hard because we deal with polyglot codes all the time. Okay, and now the question you've all been waiting for, apparently. So for the panel, if Python is the new Fortran, what's the new COBOL? And everyone has to answer. So we'll start with Doug.
Seashell.
Seashell. Haskell.
All the easy ones are gone. Pass.
I'll go Rust because as far as I know, no one ever wrote a COBOL program. They just copied another one and modified it, and I'm pretty sure the same thing happens there. So,
yeah, I was just going to say I don't think it's been invented yet, but maybe AI could help.
I'll go very left field and say Ruby.
Okay, and Sarah?
I just thought of one. Perl.
Okay, Perl. All right. Okay, Sarah, do you have an answer for this one?
I think as the non-coder on this panel, I'm going to say all of the above.
With that, I think that concludes our panel. Thanks for coming. And dinner is happening. So, thanks, speakers.